In this video, we're going to see that two solution concepts that we now know are very closely related to each other. These are Bayesian Nash equilibria of Bayesian games are very closely related to correlated equilibria of normal form games. Correlated equilibria I introduced in the last video, video 5 of week 2. So if you recall, a correlated equilibrium for a normal form game consists of a randomizing device. So a way of the players of sharing a joint source of randomness plus strategies for the players that can observe states of the device. Now, a normal form game together equipped with a randomizing device can be seen as or turned into a Bayesian game where the signals of the device are interpreted as types of the players. So under this correspondence, roughly Bayesian games for which payoffs do not depend on the types are the same thing as normal form games with correlated equilibria. So remember, for a Bayesian game, we have a payoff function where payoffs depend on all moves of all players and also all types of all players. But if the payoff functions are constant for the types, if payoffs don't depend on the types, what we get back is not ordinary Nash equilibrium, we get back correlated equilibrium, because observations of types and kind of conditioning and Bayesian updating on types still happens, and that's what happens in correlated equilibrium. So I actually like to see, personally, I like to think of correlated equilibrium as a special case of, as a kind of closely related to Bayesian Nash equilibrium, as a special case of it, rather than as an extension of ordinary Nash equilibrium. If you remember, correlated equilibrium for a normal form game is going to consist of a set of signals for each player and a joint distribution on all of the signals, plus strategies for each. So this is for a pure strategies. For a strategy for each player is a function from the signals they could receive to the moves they could play, satisfying optimality. And while making this video, I realized that when I made the video about correlated equilibrium, I actually I failed to completely define what a correlated equilibrium was. I actually forgot to write down the optimality conditions. So the optimality conditions, I'm going to go back and repair the slides. But the optimality conditions for correlated equilibrium look the same as the ones for Bayesian Nash equilibrium, namely that for every combination, for every player and for every signal that they could receive with positive probability, an optimality condition holds. So here's an example that we used. I think this was in the exercises for week 2. Think about Battle of the Sexes. So this is Battle of the Sexes is the coordination game where both players prefer to be two choices. Both players prefer to make the same choice, but given that where one prefers one and one prefers the other, football and ballet. And in the exercises, we had a correlated equilibrium of this, where each player has two signals, and the two signals, we're going to have a randomizing device where these two signals are perfectly correlated. So we're going to say with probability 1/2, the signals are both 1, and with probability 1/2, the signals are both 2. So there is probability 0 that the signals are different to each other. So we have perfect correlation. Now with this randomizing device, it was a correlated equilibrium that both players use the strategy that in type 1, they play football, or go to football, and in type 2, signal 1, they go to football, and in signal 2, they go to ballet. So it's kind of they're deferring their decision to the randomizing device, and because it's correlated, it makes the same decision for both of them. It's also a different correlated equilibrium with the same randomizing device that both players use the strategy that plays ballet in signal 1 and football in signal 2. So we can make this into a Bayesian game where both players have two types, and the payoff switch is now a function of the moves of both players and the types of both players are given by the payoff matrix, the battle of the sexes, ignoring the types. So we just take this move, player one's move, and player two's move, and plug into the payoff matrix. So our two correlated equilibria that use the randomizing device now become, oh, and of course, what I forgot to write here is that, so a Bayesian game has, part of the definition of the game is the prior distribution, joint distribution on types, and that is going to become exactly this joint distribution. The randomizing device is going to play the role of nature drawing the types of the players. So now if we do this, so now we have a Bayesian game, and our two correlated equilibria are going to become Bayesian-Nash equilibria. Namely, this is one Bayesian-Nash equilibrium, and this is another Bayesian-Nash equilibrium. So in both cases, the optimality condition says that in all of the states that could happen with positive probability, namely this one and this one, player one strategy is going to maximize their expected utility given their type, and player two strategy is going to maximize their expected utility given their type. And in both cases, because the types are completely correlated, that means that given T1, we know that, so T1 and T2 are the types of the two players. And if we're given T1, we know that T2 is equal to it. So we can calculate this expectation just by plugging in. So the expected payoff for player one, given their type, is given by plugging in player two's strategy for player one's type, because player one knows that player two's type is the same type. So we can draw this as a in extensive form. So here we have nature drawing two possible states. One is where both players have type one, and one is where both players have type two. And then we have two copies of the bimatrix game. So here, player two with information sets can't see what player one does, but things are set up so both players see their type. So both players know if nature went this way or this way. And then these come from, this is two copies of the payoff matrix for Battle of the Sexes. Okay, this last slide is a kind of addendum to this week's topic. This is and now for something completely different. So far, everywhere we've carefully avoided combining subgame perfect equilibria with basically any kind of probability. Particularly so for Bayesian-Nash equilibrium, we've been thinking about sort of subgames, namely states, combination of types the players can be in are kind of like subgames. Like here, if you look at this tree and you think about subgames, I mean, this is a subgame and this is a subgame, and these are the two things that nature can do. So they're like states. But we only consider subgames that can happen with positive prior probability, rather than all possible subgames. So going beyond this makes us confront a very difficult question, which is, if we observe an event that has prior probability 0, how should we update our prior? Bayes' law does not help you there. When you want to combine subgame perfect equilibrium with probability, you have to confront this, because if you pick some random node in the tree that doesn't happen on the path of play with any positive probability, the prior probability of being there was 0, and so you have a big probability theory headache. So this is quite important, and there's a whole branch of game theory that goes in this direction. There are quite a few different approaches to this problem, which get increasingly complicated. The simplest approach is a thing called perfect Bayesian equilibrium, which is a cross between Bayesian, Nash, and subgame perfect. And perfect Bayesian equilibrium requires us to attach beliefs, that is probability distributions, to every node in the tree. So for every node in the tree, whether we can reach it with positive probability or not, we have to say what the players will believe when they get there. And there are different variants of this where you require different different conditions. So you could require more or less about how consistent these beliefs are. So there's a whole branch of game theory that goes in this kind of direction. But that's all I'm going to say about that.